Welcome to the presentation of the Modbus RTU Slave chip. This video has two parts. The first part is about the main characteristics of the chip, and the second part is a practical video about how to implement a Modbus Slave using STM32. So for the introduction, just continue listening, and if you want to jump to the practical presentation, go to minute 10. So let's say you need to develop a Modbus Slave product. It can be to control a motor, to control the state of a solenoid, or to read the value of a sensor. So from your Modbus master device, a PLC or a PC, you will perform the appropriate function codes, the appropriate Modbus request in order to set the speed of the motor and also to read uh, its values like the current, the power, the temperature, whatever. So here you can read and write. You can write the solenoid state, or you can read the sensor data. And how do you do that? How do you add Modbus to your microcontroller or to your embedded computer, to your FPGA? So one of the easiest ways, and the one that we present here, is to use the dedicated Modbus chip IS4310, which is a chip that embeds the Modbus RTU Slave stack. It has the most typical function codes, read holding a register, write single register, and write multiple registers, and you can interface via the I2C using 3.3 volts microcontrollers or even 5 volts microcontrollers. And the I2C speed, it's the typical ones, 100 kilohertz, 400 kilohertz, or 1 megahertz. The hardware integration of the IS4310, it's quite easy. You just have in one side the I2C serial interface, and in the other side you have a UART interface that connects to a transceiver. So the Modbus chip is agnostic, referring to the electrical interface. So you can use this Modbus chip, the IS4310, with RS485, with RS232, or with RS422, or any other kind of serial interface. So just use the transceiver that you need to fit with your electrical interface. Say that almost always it will be RS485. So any transceiver can be used as long as it has the TX, RX, and detection pins. The chip is quite easy to integrate. As said, it has only 8 pins, the I2C interface, the power pins, which is powered at 3.3 volts. The I2C is 5 volts tolerant. Here you have the TX, RX, and detection for the transceiver connection, and this pin, the I2C speed pin, tie this pin to ground to set to tell the chip that you are going to use 100 kilohertz. Now, in the firmware side, how do you interface your microcontroller, your application with the IS4310 Modbus chip? And how does the chip interfaces with the Modbus Master? So think about the IS4310 as a memory chip, as a typical I2C memory chip. So whatever you write to one of these holding registers, you have actually 500 holding registers. If you are doing a temperature sensor, you read with your microcontroller the analog value, or you read anything from your sensor, and you process the data, and you store this data, let's say, to the holding register 0. So the PLC, your client, the master, your computer, to read the data of your sensor that you did store in this holding register, the Modbus Master, it only has to read the holding register 0 and will get the value that you stored there using the Modbus communications, which are all transparent to you as you are using the IS4310. Let's use an opposite example. Let's say you need to control the speed of a motor. You have a motor controller and you need to use the holding register 0 or any other, let's say the 0. You write here the speed. So the Modbus Master, let's say it wants to put the motor at full speed. So it will write 100 to this register. Your microcontroller is keeping reading the register. It reads the value and it sets the motor to 100% of speed. So those 500 holding registers are free for your use. You can use one or all of them. And we have those 4 special registers over here. So this is the Modbus address of your device. If you write here a 10, the Modbus Master must address to the Modbus Slave 10, which will be you. Remember that in the Modbus bus, there can be lots of slaves. So this is the way how you make unique from the rest of the slaves, the Modbus address. And these 3 registers over here are the typical serial configuration registers parameters. So the baud rate of the Modbus RTU speed, the parity bits, and the stop bits. This is the typical serial configuration. That's all. So just read and write the memory map. The master will do the same, and that's how you exchange the information. And forget about all the Modbus implementation. This schematic, you will find that on the datasheet. You can find the datasheet on the web page. It's a typical application, a typical hardware design of the RS485 electrical layer interface for the Modbus chip. So it's very simple. You just have your microcontroller, the pull-up resistors for the I2C, the Modbus chip, the transceiver. In this case, we are using this one, a nice one from Texas Instruments. And as you can see, it's a 5 volts transceiver. We recommend 5 volts transceiver over 3.3 volts transceiver. They reach longer distances. They have more noise immunity. So, and as the Modbus chip is 5 volts tolerant, also these pins, you can use 5 volts transceivers. This is the protection side for the RS485 and the connector. This is the same, an RS485 schematic, but in this case, an isolated one for the noisy electrical environments like factories or places where the power lines are full of inductive loads. And this is the typical RS232 example. A classical Modbus application. And okay, remember RS485 loves daisy chain topology, so stick to daisy chain topology connections, avoid the rest of experimental, don't do that. And stubs are also allowed, but it's preferred not to have them. This is a typical, more general Modbus bus implementation using Modbus Master chip and the Modbus Slave chips. You can use a PLC, a computer here. You can use any device as a slaves. It's a Modbus. It's a standard protocol. Use any device that you want as long as you feed the electrical layer interface, the baud rate, parity bit, and stop bits. And only one address different. Don't put 2 slaves with the same address. There are some firmware examples for Nucleo, for STM32 and Arduino, and also for Raspberry Pi. And you will find some evaluation boards for STM32 and Arduino, so that directly fits to those microcontroller boards, and also for Raspberry Pi, it also directly fits. And there are also some ready-to-go modules. So this is a IS4310 plus RS232 transceiver. Just solder this module to your project and it enables your project to have Modbus over RS232. In this case, that also, that's a mistake. That must be RS485. Okay, and this is the same RS485 but isolated. So thank you for listening, and yeah, you can reach any questions to the company mail. So as an example, we are going to make the typical Modbus server to control a relay. Uh, so from a Modbus client, from a Modbus Master, we will write a 1 to the holding register 0, and then the relay will turn on. And if you write 0, the relay will turn off. So simple. Okay, this is all the code, this loop code. We simply read the holding register 0, and if it's empty, we turn off the blue LED on the board, on the Nucleo board. And if it has something, the register, the holding register 0, we turn on the blue LED. That's all. Let's check that. To control our Modbus slave. So to control this is your project. This is your Modbus slave. To control that, we are going to use the software to emulate a Modbus Master, which is this one, Modbus Master. This is a super easy and nice Modbus program that emulates a master. So find where is your dongle connected. Find where your USB to RS485 dongle is connected. In my case, is in the COM8. Okay, so I go to the configuration, I set COM8. The default baud rate of the Modbus chip is 19,200, 8 data bits, 1 stop bits, parity even. This is not random. This is what the Modbus standard says that must be by default the standard configuration. So that's not the chip decision, that's the standard Modbus standard decision. So we go by the default values. By default, the chip has the slave address 1. We connect. Okay, yeah, we write a 0. We send the data. Let's be sure that the LED is okay. Let's try to make let's put this here, let's put this over here. Yeah, nice. Okay, so the blue LED is okay, it's on. Let's write it, and it's still on because if I write a 0, okay, let me flash the code. Okay. Okay, now the code is uploaded, and yeah, it's a 0, it's the blue LED is off. If I write 1, I click here to update the data, to send the data. Check that we are doing write single register function code. Okay, that's the function code 6. I write it 1 and I send the data, and the LED turns on. I put 0 again, and the LED goes off. Okay. Okay, let's check better the code. What's inside read holding register? So I just control click here. That's my mine fail, and that's just at the very top. Okay, so read holding register. It's nothing here actually. The only secret of this function to read the holding register is this. So the core or everything is the half function memory read, because the chip, the Modbus chip, is thought as a memory chip actually to make everything easy. So you just think of the chip as a memory, as an I2C memory. Therefore, you use the I2C memory functions of the hull. and you want to read something, so what do? I2C memory read. Which parameters it has? The I2C of your microcontroller, the chip address, which is 11 in hexadecimal. Yeah, remember that. If we go to the datasheet, I2C description, highlights. So the I2C device address is 11 in hexadecimal. Okay, the third parameter, register address to read. This is simply the parameter we pass off to the function. So in our case, 0. We are willing to read, let me show, the holding register 0 because we are passing a 0 to the function. Okay, so go back to the function. This parameter, we tell the HAL that our chip is a 16 bits addressing memory. So look at that. We have more than 255 registers. Therefore, if I want to address this register, for instance, I need 2 bytes. You can see this very clear here. When you actually want to read something on the chip in the I2C, you send the I2C address of the chip and then you send 2 bytes, which together represent this address, the 0, the 1, blah, 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 until 503. That's why you tell him to the HAL that you are using 16 bits addressing. This is a constant, you just write that. And you tell him where to put the result, you pass him an array, and you tell him to read 2 bytes. Look, all the registers are 16 bits long because Modbus states that a holding register is 16 bits long. So when you read a holding register, you are actually reading 2 bytes. You are reading 2 bytes to make the 16 bits. That's why you tell him 2 bytes and you give him an array that has a size of 2 or more and the timeout. That's all. When you have the information read, you just put together those 2 bytes into one. Okay, that's what you do with the read result variable. You are putting together the 2 values of this array and you return the 16 bits result. That's all, no much secret, just this is what makes all the magic, which is a HAL function. Now let's quickly review the wiring of the board to see what's everything there. Okay, let me show you the camera. Nice. Okay. So actually not much mystery there. This is our Nucleo board. We have those 2 cables that go to our Modbus chip, which is here. So pin 1 is SDA, pin 8 is SCL. We have the pull-up resistor, we used 1K, which is very low, 2Ks, which will be better, but it's fine, it will work, no problems. And what else do we have? Pin 3 and 4 is the power, so are those cables over here. This cable and this one go to the Modbus, the RS485 transceiver, are the cables that go to the DI, RO, DE, and RE. So this is the connection between the chip, the serial connection between the chip and the transceiver. No much secret, just go connect directly. This cable is the pin 7, is the I2C speed. You are telling by bringing this pin to ground, you are telling the chip that you will communicate to him at 100 kilohertz using the I2C at this speed. you pull this to 3.3 volts, you will be using 1 megahertz. Okay, and not much over there. So we have over here the USB to RS485. You have pin A and B and the common, so A and B go to A and B of the transceiver, and the common goes to ground. Okay, that's all. No much mystery. It's actually pretty simple. Only a lot of cables that looks messy and looks uh, big circuit, but actually it is not. It's just what you have on the datasheet. So let's check that quickly. The datasheet hardware examples is only the circuit. What you see here is what is on the breadboard, except by this protection, and the transceiver is the module. Just one more thing. Let me show you back the camera. Look that the power of the RS485 transceiver goes to directly to 5 volts. I recommend you to use 5 volts transceivers because compared to the 3.3 volts transceivers, the 5 volts one reach longer distances and present better noise immunity. So if it's possible, use a 5 volts transceivers. And there is no problem with the interface to the Modbus chip because the Modbus chip is 5 volts tolerance into the UART connection to the transceiver, and it's also 5 volts tolerance in the case you are using 5 volts microcontroller. So the I2C and the UART pins of the Modbus chip, it's 5 volts tolerance, but the chip goes to 3.3 volts.